Hello everyone, and welcome to our presentation on CryptoChat, our secure messaging application developed for the course. In this first section, I'll explain why we built CryptoChat, what problems it attempts to solve, and what makes it different from typical school programming assignments. We live in a world where secure communication plays a massive role in day-to-day digital life. Every time you send a message, check your email, join a meeting, browse a website, or unlock your phone, encryption is being used to protect you. But even though encryption is everywhere, most people, including many engineering or IT students, rarely see how those systems work internally. They know the buzzwords like AES or Diffie-Hellman, but they never actually watch these algorithms run, or see how they cooperate to secure a conversation. That's where CryptoChat comes in. Instead of building a normal messaging app, we focused on building a transparent demonstration of cryptography in action. When users connect, the application shows fingerprints. When the key exchange happens, the interface updates. Messages are encrypted in real time using real algorithms, not simplified versions. Our goal was not to compete with professional messaging protocols like Signal or WhatsApp. Instead, the goal was to create a system small enough to understand, simple enough to analyze, and complete enough to demonstrate real security concepts. In effect, CryptoChat serves as a teaching tool for ourselves and for anyone who examines our code, showing the life cycle of secure communication from start to finish. In today's video, our group will walk you through the entire system, how the program is structured, how each module works, how the cryptographic engine functions, what attackers we considered, the system's known limitations, and what enhancements we plan to implement in the future. By the end, we hope you'll have a solid understanding not only of CryptoChat, but of the underlying technologies that make secure messaging possible. To understand the practical implementation of CryptoChat, we need to take a closer look at the architecture. Even though the program is relatively small compared to enterprise-grade messaging applications, it's still structured into clear, well-defined modules that each handle different responsibilities. The three major components are app.py, peer.py, and cryptoutils.py. I'll walk through what each one does and how they fit together. We'll start with app.py, which is the graphical interface built using PyQt6. The UI is simple, but intentionally informative. It contains the chat window, connection controls, and security indicators. Unlike many messaging apps where security runs quietly in the background, CryptoChat brings the cryptographic process to the surface so users can actually see and understand what's going on. The UI displays the user's fingerprint, the peer's fingerprint, after connecting, and the status of the encrypted session. This helps visualize the key exchange and provides immediate feedback when the system becomes secure. Next, we have peer.py, which handles everything related to networking and communication. This module establishes the TCP connection between the two peers, allowing one to act as the server and one as the client. Once a connection is formed, peer.py manages the exchange of public keys, receives encrypted messages, sends encrypted messages, and synchronizes the nonce counter. It also handles unexpected events like dropped connections or malformed packets. Basically, if information travels over the network, peer.py is involved. Finally, cryptoutils.py contains the actual cryptographic functionality. This includes generating key pairs with X25519, deriving symmetric keys with HKDF SHA256, performing encryption and decryption using AES256 GCM, and managing the monotonic nonce counter. By separating cryptographic operations into their own module, we ensure that all encryption remains consistent, auditable, and correct. This modular architecture gives the application structure and clarity. Each module focuses on one responsibility, which simplifies debugging, improves readability, and makes the system easier to extend. In the next section, we'll take a deeper dive into how the cryptography actually works behind the scenes.
Any secure system must be built with a clear understanding of the threats it faces. For CryptoChat, we created a formal threat model that identifies different types of adversaries, their capabilities, and how our system defends against them. I'll walk through the four primary attackers we considered. The first is the passive network attacker. This attacker can observe all network traffic passing between two peers. However, they cannot modify any of it. Passive attackers are completely derailed by CryptoChat's AES 256 GCM encryption, which ensures all messages appear as unreadable ciphertext. The second attacker is the active man in the middle. or MITM attacker for short. This individual can intercept packets, change them, or attempt to impersonate one of the peers during the handshake. CryptoChat addresses this through fingerprint verification, which is also known as trust on first use. After the key exchange, each peer displays a fingerprint derived from their public key. Users confirm fingerprints match through an outbound channel. If the fingerprints match, the key exchange was not intercepted. The third attack we modeled is the replay attack, which tries to resend previously transmitted encrypted messages. CryptoChat prevents this by using a strict monotonic nonce policy, where each message must arrive with a nonce higher than the last. Any out-of-order messages is rejected, neutralizing a replay attempt. Finally, we consider the out-of-scope threats with a local attacker, which is someone who gains physical access to a device or installs malware. CryptoChat makes no attempt to defend against this attack, which is consistent with real-world messaging apps. If your device is compromised, even the strongest encryption can't protect your messages. This threat model guided our design decisions and ensured that CryptoChat defends against realistic and meaningful threats while remaining educational.
We will now show a two-part demonstration of a secure chat between a Windows user and a Mac user. First, you'll see the Windows perspective, where the user will act as a server, and make sure to pay attention as they start the application and display the unique security fingerprint. Next, you'll see the client's perspective from the Mac. The user will connect to the server's IP address and pay close attention to the trust on first use step, where both users must verbally and securely confirm that their fingerprints match. This is the step that prevents a man-in-the-middle attack. So as you see, once the fingerprints were confirmed, the session became secure and the users were able to exchange end-to-end encrypted messages.
While CryptoChat demonstrates strong cryptographic foundations, it's equally important to acknowledge what it does not provide. Understanding limitations is a crucial part of designing secure systems. The first major limitation is the lack of long-term identity keys. In advanced secure messaging apps like Signal, users have permanent identity keys that verify who they are across long periods of time. CryptoChat instead generates new key pairs each session, meaning fingerprints change. This forces users to re-verify keys every connection. The second limitation is the lack of group messaging. Group chat requires complex group key agreement protocols. Adding this would require sender keys or something like the MLS messaging layer security protocol, which is far beyond the scope of our current implementation. Another limitation is that CryptoChat uses a static session key for the entire duration of a connection. Modern apps rotate keys regularly using a ratcheting algorithm. This allows for forward secrecy and backward secrecy, even if certain keys are compromised. Without ratchet, CryptoChat has basic forward secrecy but no post-compromise security. CryptoChat also does not offer offline messaging, so both peers must be online simultaneously. Many real messaging apps provide server-side storage, message delivery receipts, and queuing, which we chose not to implement. Additionally, CryptoChat does not hide metadata. Message length and timing are visible to observers even though the content is encrypted. Finally, CryptoChat does not defend against device compromise, which is the hardest challenge in secure messaging. If malware steals your keys or reads your screen, encryption cannot compensate. Even with these limitations, CryptoChat still serves as a strong educational demonstration of a secure messaging concepts.
To conclude our presentation, CryptoChat represents a complete, transparent, and educational demonstration of end-to-end encryption and secure communication. Our project uses real cryptographic primitives such as X25519, HKDF, and AES-GCM to create a functioning messenger that showcases how modern security protocols work. Building CryptoChat taught us how sensitive cryptographic systems really are. We learned why key separation matters, why non-true use breaks AEAD encryption, and why even small implementation mistakes can have huge consequences. It gave us insight into design decisions behind protocols like Signal and TLS and helped us appreciate the careful engineering required to make secure systems work properly. Looking ahead, there are several improvements that we are planning to pursue. Implementing persistent identity keys would provide stronger authentication. Adding a racketing algorithm would give post-compromise security. We would also like to explore group messaging, offline message storage, message padding, and better UI indicators to help users understand their security state. Overall, CryptoChat accomplishes what we set out to do. Build a lightweight but realistic secure messaging system that demonstrates modern cryptography in a way that's both understandable and educational. Thank you for watching, and we hope you found this presentation informative.